Okay, let me recall you that last time we have seen that if U0 is given in C2, so U1 V0 is given in C1. Then there exists a unique solution to U in C2 1 over C squared UTT minus UXX equal to 0. Maybe we can just study the problem for positive times for simplicity. So let us write the problem for positive time. Okay, today. U of 0x equal U0 of x, ut of 0x equal U0 of x, this and the solution was given by, this was an interesting formula, it was an mean value and then do you remember this formula? So we have the superposition of two waves, this wave called direct wave, this is called inverse wave, and a contribution due to the initial velocity on the integral so U0 here and the value of and the integral over this interval of the initial velocity. So let's do some, before we're going into another more general proof of this fact, let me do some qualitative analysis in order to understand a little bit better this expression. So suppose for simplicity that V0 is equal to 0. So this term is not present, and suppose that U0 of Tx has the following form. So it's an even function, it's an even function. So this is the graph of U0, and the constants are, so U0 is U0 of x is equal to x, the constant is alpha, x plus alpha if, so this is minus alpha, this is alpha. So if x is here, minus alpha is less than or equal than x equal than 0. Okay, then minus x plus alpha if 0 less than or equal than x less than or equal than alpha, and 0 else. So the graph of the initial function is this one. Now there is a small problem here, that this is not C2. Okay, so U0 is not 2. U0 is just Lipschitz. So we are not, strictly speaking, allowed to use this formula here, right? But suppose that we, for the moment, just take this. Suppose that this is still true. Suppose still the validity of 1. Okay. I will try to draw for you the solution, the graph of the solution, like a movie as time passes. Okay? So, first of all, time. So let me try to draw something like this. So there is minus alpha and alpha. So these are the time slices. Okay, so time t equal alpha over 4c. So out 1/4, 1/2, 3/4, 1/5/4 t equal to 24. Okay, first of all, the graph of the solution at this time is the following. If you write time equal alpha divided by c here, what do you get? You get 1/2 u0 of x plus time is alpha over c plus u0 of x minus alpha. So this means that you have to translate your function, your initial function here, you translate this on the right by the quantity alpha. So you get this. You get this. and then 0 else. And this instead is, you translate on the left this of the quantity alpha, so you get this and then you divide it by 2. Okay? In intermediate times, it is of this sort. Say, this I try to write, say, not so easy. This second one maybe is easier. The third one is maybe not so difficult, maybe. Because this you have to imagine to superpose these two tensors, these two triangles, then you have to divide by 2. So the second one is a sort of object obtained by superposing this and this. I'm not sure that. So you have these two waves. So this height is this height here, right? Because then you have to divide by 2. Okay. So this is going traveling toward the right, traveling toward the left. So this is slightly moving toward the right, toward the left. Then you have to sum the two, this plus this plus this, all the vertical components of the two, then divide by 2. Okay. So this is okay. This is correspond to this. Sorry, the picture is not perfect because I'm dividing by 2. So this should be half of this. This height should be half of this. It's not really like this, but more or less. And also here. Then the third one. These are starting moving, and the mean value is more or less something like this. After time passes, then you can imagine it's more easy because now the waves do not see each other anymore. After this time here, this travels toward the right, this travels toward the left, and they don't interact anymore. Can you see it? This is the last time of interaction if you want. So then we have something like this you can do by yourself, if you want, I do for you. Okay. Minus 12, maybe here. Oh, this was I have to write this in just here. It clearly is 12 and this is minus 12. Okay. Instead, this is so this is 2 alpha. This is 3 alpha, this is minus 2 alpha, this is minus 3 alpha. Okay, then we have here a triangle. And then our solution is half of it. Okay. Still remains to draw the time 3 over alpha, so this is something like intersections here. Let me draw just something like this. So this is a sort of movie in which the most interesting fact interactions appear up to this time. After that, they travel independently, one on the right, from the right, the other from the left. Okay, as I told you last time, we have several possible pictures to imagine this solution, at least when space-time is one-dimensional. The movie picture is not bad in order to understand. But there is also another way. No, I don't know. I think I cannot use this part.
You can use all.
All? I can use all?
Yes, so
I can use all. Okay. Nice. So let's do instead. Okay. So this is the situation. Now, here for simplicity, I took an even initial condition, right? But now suppose that our initial condition is instead an initial condition. Now suppose that U0 is supported. And it's important here that the support is compact. So 0, 0, and not 0 in a compact interval. Suppose that the 0 is supported in some interval, say now alpha 1, alpha 2, which is not necessarily symmetric with respect to the origin. Okay. Now we can draw. So this is say alpha 1 and this is alpha 2. So this it is x and y, say x and u if you want. Now we can draw instead t and x, and we can write the characteristic lines. Okay, x plus or minus ct, these lines, and here there is time. So, and there are various regions, so say region 1, region 2, region 3, say region 4, region 5, region 6. Now in time space. Now, in this half strip, what do I see? Okay, here there is the time corresponding to this time. After which there is no any more interaction. So in this region 6, what is the solution? So remember, B0 is 0, and U here is how in this region 6? And U is, it's not difficult to see how is U in region 5 and in region 4. But remember, here you have a wave traveling toward the right with compact support. The initial condition U0 is compact support. So what do I see here? U. 0. Here U must be 0. I am outside the time-space strip. No? And since we have the compact, the support is compact, so here U must be 0. And here? 0. And here? 0. So this essentially corresponds to what I see, to these regions here. And this corresponds, if you want, to this region here, and this corresponds to this region here. Is it clear? However, there is an interesting, and the most interesting region maybe is region 1. Region 1 is what happens in this part when the two waves interact together. So here I see, say, if you want, I can draw the wave, the direct wave. Here I see the direct wave. Here I see the inverse wave. And they interact here. It's not easy, but it's very interesting. This formula, even if when this is 0, by the way, for simplicity, it's really very interesting. In one dimension, one space dimension. So this is direct wave, this is the inverse wave. Okay, so this is the analysis, some qualitative analysis when just only this term in the D'Alembert formula is present. Now let's see instead what happens if I have only the velocity which is non-zero while u0 is 0. Okay, so u0 is 0. Suppose now instead so we have to remember, I have to remember that unfortunately this picture was taken for so simple. The first one picked, the red one, is when u0 was not C2. So let me write it here that I want to comment a little bit about this, otherwise I forget. So okay, so now let us suppose that V0, U0 is 0, so that we have just this expression, which is now it's not exactly it's not exactly the superposition, because there is this minus sign here. If you want, I can normalize. Okay. Okay, I can normalize, and well, capital F is just any primitive right? Any primitive, so if I take this difference, I just integrate from this interval to this. So it's similar, very similar, it's very similar to previous case, apart from the minus sign. Okay, and also I am dividing by 2c, is positive constant instead of 1, instead of dividing by 2 by 2c. So I still have sort of superposition in some sense of a direct wave, capital F, minus, however, now superposition with the minus, not with the plus, and with the inverse wave still. So in this, suppose that we had a function like this. Suppose that this is V0, simplicity. So, for instance, I have one primitive of this, one primitive say one primitive of V0, one primitive say 0 and 0. So this is the derivative of this, okay? This is the derivative of this. So here the derivative is 0, so this means that this function is constant. Let us fix this constant equal to 0, which means we fix one primitive. Then I have positive here, positive, linear, so I have two arcs, two parabolas. Okay, parabolas, and then I have constant. Okay, so which is now the difference? You see now, the point is maybe the most different situation happens in which region now? In situation, I think here, this is not true anymore. This is not true anymore. Now there it is a constant. And this is the constant 1/2c integral from alpha 1 to alpha 2 of V0. Okay. That constant is instead of 0 in region 6. I think it is the biggest difference. Okay, so this is for the analysis, qualitative analysis of our D'Alembert formula, and then I left an exercise, I think, last time. I mean, not really nice, it's a theorem. No, maybe before I have to say something about that U0 in C, which is not in C2, no? So, maybe it's a little bit too much, but still, in such situations, we can still define what is the distributional solution. Because at the end, this function is piecewise linear, at least here, you see this is piecewise linear. So it means that there are lines in time-space along which the solution is not differentiable, right? So, we cannot interpret this PDE pointwise at any time and at any point, so we have to give some other notion of solution. We have seen this already in the first order case. We have realized that in that case it was not convenient to interpret the solution, the PDE almost everywhere, you remember, because we found too many solutions almost everywhere, and we decided to use another notion, a weak solution. In that case, it was the distributional solution. So we do the same here. We can give a definition of distributional solution, similarly in an open set, if you wish. So definition, omega say an open set of R times R. We say U is a distributional solution to our problem, to the wave equation. If, again, the idea is simply, since the PDE, you can remember, no? So which is the idea? We have, we could put also the Laplacian, but let's do this in one space dimension. So if I multiply this by a test formally, if I multiply this by a very smooth function, then I can integrate by parts, putting all derivatives here, and then here I have to integrate twice. So I have two changes of sign, and so the sign does not change at the end. Minus minus is plus. Also here, minus 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 remains minus. And I have boundary contributions, but if the function has compact support in an open set, I cannot see any boundary contribution. So, and in this way, for any test function now, say C infinity, compact support, what is important is the support here. Because that is the support, you remember, that determines the choice of the support determines the validity of the PDE. If necessary, that determines also the validity of a boundary condition. Because you remember that for first order PDE is how we got the validity of the PDE. Now I don't remember how it's called. Maybe the initial condition U0. How we got this condition in the first order? Well, we choose test functions which were 0 at time t, capital T, but not at time 0. Not at time 0. Otherwise, we don't see anything. No? Remember, that was why we introduced that space. This function were test function, but possibly non-zero on sigma. Now, if we do not impose any boundary condition, we just look for a solution, free solution without boundary condition. And the clever thing here behind this is that now there is no anymore any derivative in this expression of u. So all derivatives are on the test. Test is smooth, compact support. This is an integration of a compact set using a non-local, and this integral is well defined. Okay, this is the usual idea. Okay. For any test function. So now a good exercise would be, in order to somehow, how can I say, in order to think that even if the previous function were put that was piecewise linear because it's easy to sum with traveling waves, direct and inverse, that was still correct. Let me try to do the following exercise. So, exercise. So let capital F and capital G be two log functions. U of tx defined almost everywhere is a distributional solution. So this means that our expression that was exactly this, now in that case, this was U0 and it was Lipschitz, so much more regular than M1 But in any case, this, if this is true, this at least shows that this object is still a solution, at least in this sense. So it's interesting in any case the previous discussion. Okay, so how to prove this exercise? So what do we have to show? First of all, we require this integrability, and it is clear that this expression is still in L1 log. Okay, so U is in L1 log. So what do we have to show? So we have to show this. We have to prove this. Okay. So now let me introduce a change of variable. As you can imagine, change of variable is phi from R2. I'm trying to mimic also the notation similar that we. Now the change of variable is different from what we did in the case of characteristics, but somehow I'm trying to mimic the same notation, so psi and eta. So this is psi x minus 2c psi plus eta divided by 2. And this is tx, coordinates tx. So we have already, the idea is simply, let me write the idea. Implement the change of coordinates transforming that we have seen in the C2 case transforming the wave equation into, do you remember, I think it was -4, something like this. There was a constant here, dv. Do you remember this change of coordinates? It's like taking as new axis the two characteristic lines. So now we have to implement the same idea, but we interpret the PDE in a different way. So the idea is simply to rewrite this PDE, this integral, into the new coordinate system. So instead of integrating dt dx, now we want to integrate dxi deta. That's all. Okay. So it's just an integral version of this transformation that we made last time. Okay, so the determinant, this is invertible, the determinant of the phi, I think it was 1/2c. So now what do? We simply, so now I want to show that this is still a distributional solution, so I have to put f plus g here in place of u. So let's do the computation, so this is linear, let's do the computation just for f, because the same similar computation holds for g. Okay, So what do I really have? So we do the computation only for f. The transformation of the integral, okay, the computation only for f, in the case of g being similar. So I fix phi in C infinity C r times r, and then I use the notation, I think, phi hat. So phi of tx is phi hat of psi eta. Okay? So I simply write phi hat. So I am in the space, this psi eta are on the left. My initial integral is on the right, coordinates dx. I want to write everything in integral on the left, psi eta. So this phi hat means that is the composition. I first start from here, then put this here. So I just do just something like this. And then, okay, so I fix this, and then I write this double integral over r times r u 1c squared pdt minus pxx. As I said, for the moment, let us consider just only capital F, the inverse wave, so, and then we have 1 over c squared phi dt minus phi x. And then I change variables, so I just use the fact that here I have a determinant which is constant, so I think that there is 1 over 2c outside. And then I have to compute this operator in the new coordinates. I think that it is really minus 4, I hope, check, 1 over c squared phi pt minus phi xx, I think should be minus 4. I think should be with the minus 4 and no c squared around. I hope. So check this. So it should be, there should be no c squared c around. So I have the determinant, which is constant, then I have minus 4 here. And then I have the double integral, and then I have f of psi, second derivative of phi hat, psi eta, psi eta. So this is simply a change of variable in double integral. Okay. Now I first integrate inside that, so this I can write, of course, as f of psi using the Fubini-Tonelli integration. So here there is a constant, so minus 2 over c maybe. The important fact is that this constant is non-zero. So it's the second derivative phi hat psi eta. So now psi. So now let us concentrate on the inner integral.
Is it 0?
Yes. Why? So so I think I have minus 2 over c, then I have f of psi, and then what I have here, I have just the derivative with respect to eta of something. This something is phi hat psi, right? Psi. And now I can use the integration fundamental theorem of calculus, and this phi hat has compact support. So when I compute this integral at plus infinity, quote, it's 0 minus 0, because phi hat has compact support. So this is 0, because phi hat has compact support, because such was phi, and therefore also phi hat has compact support. So this is integral, this integral is 0, the result is therefore 0, and this is exactly what we want to show.
In the case, it's not the full R, the F and G are not, everyone just in a subset of R. Will the result remain?
Subset of R, I mean, if you want to write this, I think that omega should be, for simplicity, convex, at least. Or maybe omega intersected, these lines must be connected, and omega intersected this line must be connected. Suppose this, omega convex. Then the result remains. But if your omega is very strange, like this, and this is a characteristic line, no? Then, and the intersection is not connected, then it's not true anymore that a solution can be written as fx plus ct plus f plus gx minus ct. So we need some something, say convexity. I think it's better. It's better to have. Otherwise, I think that if we take, and that's unfortunately for me, it's an interesting question. No, it's a good question. By the way, just joking. And, suppose that your domain is maybe some. And these lines are characteristic lines, parallel to characteristic. These are characteristic lines. They are parallel. Something like this. So maybe function which is something like u equals 0, here this is x equals ct, this line is x equals ct, okay? This is the origin. Sorry, the drawing is terrible, so I can invert. So this is not convex. This is omega, not convex. These are characteristic lines, and also this. Okay? Now, if I take here something like this. U Tx So you see the intersection, and of course is not connected. Maybe this is a solution or a C2 solution which is not of the form D'Alembert. C2 because I take the power 3 larger than 2 here and power larger than 2 here. So along this line I have 0 and then something which here is sort of cubic. So cubic and 4 order. And 4th order polynomial, so here it is surely C2, right? So the square would not be sufficient. But it's not of the D'Alembert form. Okay, now the last time this was just useful sort of remarks, but last time there was an interesting representation claim, interesting representation formula. So let me try to rewrite it. And maybe I don't remember the notation. Sorry, if you can help me. So theorem, representation formula. I think it was something like so we have Tx and we have this point here, this point here, and we called, I don't mean triangle, so triangle Tx. Or something like this. And so if we take an open set, so let U be C2 in omega. Omega open contain the closed triangle. So fix Tx. Fix Tx. Let use it. Let Tx be the closed triangle as in the figure. Omega contain Tx. Then we have, this is the sum of 3 terms. I think one is what we expect. So what we know to be there. Okay, this is what we know to be there. Second one is name for this one. And then, however, there is something here, and then there is something that this is, say that this, it is how we fail to solve the equation. How much we said we failed to solve the equation. So was this the statement? There is a constant here in front. The constant. There should be some constant here in front. Which constant? Some constant depending on C. Maybe there is 1 over C. Something like 2 over C? No, not really. Now the constant. C over 2. Let's see over 2, right? C over 2. Okay, there is this constant. Okay, so this is a representation formula. So here, the interesting fact of this formula, if it is true, now let's see, is that U does not solve any kind of PDE, just a smooth function into variables. Okay. If U happens to satisfy the PDE, then this error term is 0, and we get the D'Alembert formula. So clearly, this is a general. If it is true, it's a generalization of the D'Alembert formula, right? Okay, so let's see if we can try to prove this. So the idea is, as usual, to use the divergence theorem. So we have to look at our PDE as a divergence in time space. Okay, so as I said maybe already last time, 1 over c squared UTT minus UXX is a divergence. Is a time space divergence. So of what? Is the time space divergence of the vector okay, just this vector field here. If I take the vector field 1 over c squared ut, comma, minus 1 over x, I take the time space divergence. It means I have to take the time derivative of this plus the x derivative of this, which is the operator. Okay. So, let us integrate over the triangle. So let me note for simplicity, t and x are fixed. So this is, for simplicity, our triangle, which does not move anymore. So that's fixed, and I call it t. So if I integrate over t, so 1 over c squared utt minus uxx dt dx, this is the divergence. Divergence of this vector field here. Okay, the triangle is Lipschitz, bounded. Okay, so T is Lipschitz and bounded. Lipschitz, bounded. So it falls within the statement of the Gauss theorem that we have given in our course. Also, this is a vector field which is of class C1. Okay, so it's of class C1 actually on the closure. So this vector field is C1 on the closure. T is closed, so it's C1 on T. What does it mean? means that it has an extension, it has this C1 extension of on an open set, which is exactly, so this vector field is C1 in this open set, so in particular is C1 in this closed set. Okay, so we have normal traces, no problems on the traces. Okay, so our Gauss-Green theorem, remember this, the Gauss-Green theorem, if we use the exterior unit normal, the exterior, then we don't change sign. Okay, so we have the scalar, just the normal flux of the scalar product ut minus ux, scalar product. So let me call it, let me call nu equal ut mu x outward unit normal to the boundary, outward to the triangle, unit normal to the boundary. Okay, so this is nu. Okay, and we have to integrate this normal flux. So this is integral on the boundary of T. So now I'm using the one-dimensional Hausdorff measure, which is just the line integral in this case, nothing mysterious, no? Just when I integrate line integral of a function. No mystery in this expression. So we have a scalar product of this times this plus this times this. 1 over c squared ut minus ux dh1. Okay, so now the point is that we have, as usual, to compute the three normals, and this is the sum of three contributions, because it's an integral of the boundary of a triangle. So is an integral on the basis, and then on the integral here, then integral here, and integral. So let me call this side, let me call the left one, let me call this the right one, and this the basis. Okay, so this is just the sum of three objects. This is equal to integral of the basis, which is easier. So 1 over c squared ut minus ux dx dh1 plus integral over the left ut minus same object dh1 plus integral on the right side ut minus ux dx. Do you agree up to now? Well, so now we have to compute the three normals. On the basis, it's easy. The time component, which is the first component, is -1. And the space component is 0. On the other hand, here I have two positive components, and here my time component must be positive, and my space component must be negative. Okay? So here time component positive but space negative, here both are positive. So, and the computations are that the two normals here are, here is c minus 1. Let me check. Yes, the space component is negative, and I have to normalize. Okay, 1 plus c squared. Should be this one. Okay. And here instead is C1, both are positive, divided by 1 plus C squared. So now we have the three normals. Integral on the basis. On the basis, the x component of the normal is 0. Everything, the normal is all vertical, and this is minus 1. So if I'm not wrong, this is minus 1 over c squared ut d. Now dh1 is simply here dx. This is horizontal segment. The measure is always this. So this integral is actually the integral from there is a minus over c squared. Okay, from x minus ct, x plus ct, and there is a minus 1 over c squared. There is this minus, which is very similar to this expression, but not exactly, because here there is a different constant in front. Okay? Plus integral over L. Now, as I said, on the left we have a negative space component, but positive time component. So we have 1 over c squared, and then here we have ut times c divided by the square. So let me put the square root here. 1 square root 1 plus c squared. The space component, we have the time component is c, and here instead we have minus 1, so apparently it is just ux dh1. And the other one on the right side we have, please correct me if I'm making mistakes, so there is 1 over c squared, then we have c ut, and then there is minus ux. Left. Yeah, should be this one. So let us just make a small simplification here. So this is just C, and this is same thing. And this is simplification. Now I have to integrate in the H1. How do I do the computations in the H1? I have to parameterize the segment, I define any parameterization, and then I integrate in the space of parameters. The parameterization that I use to parameterize L, so let us parameterize, so in order to compute the integral over L, we parameterize, as you do when you do surface integral, line integrals. Now you parameterize the curve and then you compute the integral. So we parameterize L linearly, and so by the map L from 0 to t, so maybe I use this as a parameter, okay, and then at each point here I associate a vector in the plane, which turns out to be tau, so L from 0 to t, tau So which means that clearly, essentially, I look at this segment as a graph over this, right? Graph parameterization. Any tau here goes here. This point is still tau, and then the x-coordinate, which in this case, if I'm not wrong, is x plus c tau minus t. Okay? So how do I do? This is the standard computation. So I have to compute L prime, okay? L prime, the velocity vector of the parameterization, the norm of the velocity vector of the parameterization. So since L prime is equal to 1 comma c, no, so L prime is square root 1 c squared. Okay, and this should kill this. No? So this object here. No? So when I do the computation, I get 1 over integral over L of 1 over c ut plus ux. H1 is what? Is 1 over this. So what do I do? I have to integrate on a manifold, I parameterize it, and my integral becomes an integral of parameter spaces. I have, of course, to add the modulus of the determinant. In this case, is this. No? So this becomes an integral in the space of parameters. Parameters like this. Then I have my velocity vector, and then I have the same thing. UC plus UT plus 1 over c, sorry, plus UX. Let me check that I'm doing this is computed in the parameters. So maybe this was called L, so maybe it's better to write it explicitly. This is computed in the map. So units L of tau okay. So now I have a cancellation. So I'm writing this COT, UT evaluated at L of tau divided by C. Tau. So what happens if I try to see this as a derivative? So what happens if I do T over d tau of u over L of tau? Maybe at this point it's better this 1 over c to put it here and to multiply by c. And now this is exactly the derivative of u over L of tau. No? Because if I compute the derivative of u over L of tau, what I get? Ut times evaluated L tau, L prime of tau, which is 1, and then the other c is due to this. So what I get exactly is I think it's correct, there is a 1 over c outside, and then I get d over d tau u over tau. But then this is equal clearly to 1 over c u over log t minus u over 0. Sorry, this is closed. Okay. So u over log t is just tx. So this is equal to 1 over c u of tx minus u of 0. U of 0 x plus c x minus c tau 0. So apparently, so let me go on here. For the moment, what do I get? I get that what I want to compute, this integral here, is equal to, so I have already computed this integral on the basis. Where is it now? The integral on the basis is just here, no? So minus 1 over c squared x minus ct x plus ct ut y y, and then I have that the integral on the left side seems to be 1 over c u of tx minus u of 0 x minus ct, and then it remains to compute this. Now, with a similar computation with a different parameterization that maybe I tell you, so we parameterize r, which is a difference. Now I copy it from here. So I still write it r as a graph over this segment. So tau goes into tau, and then I have to find the height. And the height is simply minus, I think here. The height, there is a minus. Now, this does not affect the speed of the parameterization, so we still, I mean, the norm of the norm of the velocity, so still we have the square root, which cancels that square root there. But we have a minus here instead of a plus, and this minus for some reason gives us, please check at home if you want, minus. So it seems that at the end, what do we get? We have proven what? We have proven that if I integrate the divergence of the triangle, so without multiplying by c over 2, so if I integrate the divergence, utt minus uxx dt dx, this turns out to be, so now let us multiply this by c over 2. Okay? If I multiply this by c over 2, then this means that I have to multiply this by c over 2, this by c over 2, and this by c over 2. Okay, let's do it. Minus 1 over 2c, the integral of the velocity, ut 0y dy. I have to multiply that by c over 2, so I have 1/2 plus 1/2, and then I can put now this together with this, and this together with this. So let me put, so there is a minus. There is a minus, 1/2, u of 0 x plus ct plus u of 0 x minus ct. And then there is, I have multiplied by 1/2, so 1/2 and 1/2 is plus u of dx. Right? Huh? I think that now it's enough to put on the left hand side this, and we have the formula. C over 2. Okay. This is curious. Now, I leave you as an exercise. So I have done this. I've chosen this triangle for my convenience. Now I give you an exercise. So the exercise asks, instead of choosing this triangle, so now fix tx, and now let us consider t plus tx, which is another triangle. Which triangle? Which triangle now? So you say that this is 2t, okay? So instead of taking this triangle here, I take the upper one. No? Just I reflect the previous triangle, I reflect with respect to this line. So let me call this triangle t plus tx, and this is omega now. So I'm asking if we can. So what happens if I want to express now the value of u here, using the value of u here, here, and the speed integrated over the upper basis now. So I am asking to you which kind of, I don't know, now I don't know, which kind of formula do we get? Why I'm asking this? Oh, I asked you to do the computation, I didn't do this. I expect a similar formula. I expect, but I didn't do the computation, so I expect this to be like this, maybe this to be, now we have this point and this point, so new points, 2t, the corresponding point here, etc. But I'm not sure about the sign, maybe this is a minus, I don't know. So please check if you have done. It's exactly the same computation as we have done here, but of course there is the problem of not making mistakes in the sign of the normals. It's easy to do mistakes. Also because t actually is vertical, but it is the first component. So I'm not used to that, using the first component in vertical, so sometimes very often actually I make some confusion. So So why I'm asking this? Because I would like to see now if there is such a formula, and we have the formula that I have previously written, it means that the value of u here should be the mean somehow of the values of 4 points, because now I can add the two formulas, right? Suppose that now I have a solution of the wave equation. This is not present. So it means that our u at x is the sum of this plus the other one. So 4 values. Curious. And then contribution of the ut of the time derivative, so the derivative in this direction, along this and this, maybe with the minus, the upper one, I don't know. Okay, so the formula somehow becomes a little bit more symmetric. Because you see, when you have utt here, this derivative does not see the change in time into minus t into minus t. It does not, is not seen by this operator. It does not, because the minus times minus is plus. So we can always go back and forth in time. So why I'm doing this for previous times instead of future times? I could do it. No? This is quite different with respect to the heat equation. The heat equation is this. The heat equation is this. It's completely different operator. There is another theory, another story. And we cannot, absolutely cannot do the change t into minus t. Because if you do t into minus t, you change this, and the operator is it's another story. Okay, but as soon as we have two derivatives in time, this can be done. So why not asking the question of looking at upper triangle instead, upper cone? No. Physics call this maybe forward cone and backward light cone and forward. No. Forward light cone and backward light cone. Not sure. Okay, so I think now. Time is over for the next argument. I would like to show the next time tomorrow. Actually, I want to relate. We have seen already the relation between the wave equation and the first order transport linear equation, but it is interesting also to observe, in my opinion, that suppose that you have a solution of this. So suppose that you have a vector uv suppose that you have a solution. So this now goes, say, from R times R into R2. So what is this? Now this is a system of linear first order PDEs, right? If everything is moot, we can relate this to our solution of the wave equation. Why? Suppose that I differentiate this with respect to t, I get this. And suppose that I differentiate this with respect to t, vtx equal ux. No, suppose that I differentiate this with respect to x, so this is uxx. Since we have smoothness, these two are equal, so this implies that, now okay, I could normalize with c squared, but if c equal 1, say. So you see, curiously, we have transformed. We have observed that a solution of this system provides a scalar function which is the solution of the wave equation. But this system is a system of first order PDEs, linear transport equation. So what can we say about first order system, linear first order system? So I will tell you just a few things, very, very small thing about this big problem of systems of first order PDEs. This is another connection with the wave equations. By the way, do you remember this system of two PDEs reminds you something? The Cauchy-Riemann. Which is the difference with Cauchy-Riemann? The second one is a minus. The second one is a minus. So, and indeed, what happens? It happens that if you put a minus here, you don't get, so you get a minus here. So you get another operator, you get the Laplacian, you get the harmonic functions, solution of the Laplacian. And the Laplacian is this. Another completely different operator, in place of the minus we have the plus, another thing. Okay. So this is what we will do tomorrow.